Let's fit a model to some data. These are the annual temperatures for the last 120 years in a fictional Midwestern town. There's 1 point per year, the annual median of the daily high temperatures. And when we look at it, our eye is really good at pulling out a pattern. There's a clear lift toward the right-hand side. We'd like to capture that in a model. There are a lot of models that can represent this, but a really nice starting point, because it's so simple, is a straight line. Here's what the best fit straight line looks like. It does a pretty good job. We can see that it definitely captures the upward tilt of the data, but it doesn't capture the bend in it. It's clear when we examine it that a straight line doesn't do quite as well as we would like. Luckily, we have a lot of other options. A reasonable next candidate is a quadratic, a polynomial with a squared term instead of just a linear term. These have some curvature to them. We can see that the best fit quadratic clearly captures the lift at the right-hand side of the plot and the bend in the middle. But it also imposes a little bit of lift on the left-hand side of the plot, which is not obviously reflected in the data. So we can try other options. We can try polynomials with cubic terms, powers of 3. Or we can look at polynomials with quartic terms, powers of 4. We can also fit polynomial models of order 5, polynomials of order 6, 7th order polynomials, and 8th order polynomials, also called octic polynomials. Useful tidbit for filling lulls in conversations at parties. Now the fit appears to be getting better, but the line is taking on extra personality. It's adopting some wiggles. If we take this to an extreme, we can imagine a model that passes through every single data point perfectly. This model would have zero error, zero deviation from our measured data. So does that make it the best fit model? Models are useful because they allow us to generalize from one situation to another. When we use a model, we're working under the assumption that there is some underlying pattern we want to measure, but it has some error on top of it. The goal of a good model is to look through the error and find the pattern. The most common way to do this is to split our data up into two groups. We can use one group to train our model, and then we can test it to see how closely it fits on the second group. The first group is the training data set. The second group is the testing data set. There are lots of ways to do this, and we'll revisit them later, but for now, we'll randomly sort out our years into two bins. We'll put 70% of them into the training data set and 30% of them into the testing data set. Then we can go back to our collection of model candidates and try them one by one. Here are a few of the models trained on the training data and plotted against the testing data. As the models get to be higher order, we can see that the wiggles they developed may have been helpful for fitting the training data, but don't necessarily help them fit the testing data better. We can see an extreme example of this in the full interpolation model, where we just connect all the training data points with straight lines. It really struggles to match the testing data points. It's helpful to look at the error on the training and testing data sets for each model lined up side by side. Looking at the errors on the training data set, a few things jump right out. First is the wide gap between the training errors, the hollow circles, and the testing errors, the solid circles. Right away we can see that there's a substantial difference between the two data sets. Second, there's a precipitous drop in error going from a linear to a quadratic model, that is a first to a second order polynomial. This makes sense. When we were eyeballing it, we could see that the linear fit failed to capture the curvature of the data, one of its most prominent features. The quadratic curve captured that just fine. So which model fits best? when we look carefully at the errors on the training data, it appears that the error on the fifth order polynomial is the lowest. The differences are subtle, so you might have to squint. But all the other higher order models have low error too. They're just a little higher than the order 5 polynomial. But as we mentioned, that's not the ultimate test. The error on the testing data is what we really care about. Careful inspection of testing error shows that the fourth order model does the best job. At higher orders of polynomials, the error on the test data set goes up. The more wiggly the line gets in fifth and higher order polynomial models, the more it captures the quirks of the training data rather than the underlying pattern of the testing data that we're interested in. Based on this train and test approach, we have a clear winner. Of all the models we tried, the fourth order polynomial is best. Congratulations to us. We chose a pretty good model for our data. But don't leave just yet. There are some pretty important ideas still to mention. Join me for part 2, where we'll talk more in depth about what we want in a model. A model is a story we tell about our data. It's always different from the data itself. It's a simplified version, a cartoon picture. It's got bold edges and even shading. There are always a lot of stories that can be told using the same data set. When we're building a model, we're making the assumption that our data has two parts, signal and noise. Signal's the real pattern. It's the repeatable process that we hope to capture and describe. It's the information that we care about. The signal is what lets the model generalize to new situations. The noise is everything else that gets in the way of that. It's the imperfections in our sensors, it's typing things in wrong, it's variations driven by forces that we can't or don't try to model. It's just all the other stuff. It's easy to picture the difference between signal and noise if you imagine listening to your favorite playlist in the middle of winter while there's a heater blasting nearby. The music's the signal. That's the thing that you want to track and absorb. The heater fan is the noise. It's the additional variation piled on top of the signal. And if it gets too loud, it becomes impossible to follow the flow of the signal. It's the goal of models to describe the signal despite the noise. A perfect model describes the signal exactly and ignores all of the noise. If a model fails to capture all of the signal, that type of error is called bias. If a model captures some of the noise, that type of error is called variance. Too much bias in our model means that it will perform poorly in all situations because it hasn't captured the signal well. You may also hear this called underfitting. This was the case when we fit a straight line to our temperature data. It didn't capture the underlying pattern well, and because of that, had a much higher error than the rest of our candidates. A linear model fit to this data has high bias. Too much variance in our model will also cause it to fail. It won't generalize well. Instead of capturing just the pattern we care about, it will also capture a lot of the extraneous noise that we don't care about. The patterns in the noise will be different from situation to situation. When we try to generalize and apply our model to a new situation, it'll have extra error. This is also called overfitting. The more complex our model, the greater the risk of overfitting. This was the case in our connect the dots interpolation model. The way to protect against underfitting is to try several different types of models. Each model has its own strengths and weaknesses, things that it's good at, patterns that it finds more easily and more accurately than others, and other patterns that it struggles with. By trying a variety of models, we have the best chance at pulling out the patterns hidden in our data. Our best defense against bias is a rich pool of candidate models. To protect against overfitting, we make sure to test how well each trained model generalizes. After training it on one set of observations, we then use it to predict the pattern in another set of observations. If the predictions are accurate, then we know our model's good and our variance is low. But if it makes much worse predictions on the test data than on the training data set, then we know that the model overfitted the training data, that it captured a lot of noise rather than just the signal. Okay, we are really getting warmed up now. Next, in part 3, we'll consider the question that can make or break our model selection: choosing the right error function. When we go to fit a model to some data, it's easy to overlook the choice of error function. Fitting a model is an exercise in optimization. It's finding the set of parameter values that minimizes a loss function. If you need a refresher on all that, check out the How Optimization Works series. There's a link in the comments below. The difference between a model and a measured data point is called deviation. And the error function expresses how much we care about a deviation of a certain size. Are small errors okay, but large errors really bad? Or is being off by a little just as bad as being off by a lot? In business terms, we can think of the error function as how much it costs us in dollars to be wrong by a certain amount. In fact, error functions are also called cost functions. The choice of error function depends entirely on how our model is going to be used. So first, let's think about the case where our temperature predictions are being used to design a greenhouse. The thickness of the glass and the amount of insulation around the base of the greenhouse are carefully selected to create the ideal growing environment. There won't be any heaters or air conditioners to modulate the temperature, just passive heat flow determined by the design of the greenhouse. The plants are hardy and can tolerate being off by a few degrees in any direction fairly well. It stunts them a little, but not catastrophically. However, the further the temperature gets from the ideal, the more detrimental it is to the health of the plants. And quickly the effects become more severe. This suggests that the cost function is something like the square of the deviation. Now consider another use case. Now we're designing a greenhouse again, but this time we're including heaters and coolers. This means that we will be able to modulate the temperature to make it suitable for the plants. But the more heating and cooling we do, the more energy we'll have to buy, and the more money we'll have to spend on it. So the cost of being off in our prediction is related to how much it costs to correct for it. The energy cost to bring the temperature back to the appropriate range. This suggests an error function where the cost is proportional to the absolute value of the deviation. All of the models fit to our temperature data in part 1 used an absolute deviation error function. Now let's look at a third use case. Here, our temperature forecasts are now being used to make decisions about when to preheat or pre-cool an office building for a workday. Preheating and pre-cooling during the night allows a lower energy price and saves the company money. The cost of any deviations is the additional cost of daytime peak energy. This is proportional to the amount of time the equipment runs during the day, which in turn is directly proportional to the prediction error. However, above a certain prediction threshold, no amount of time heating or cooling will fully make up the difference, so the cost has a ceiling. The equipment just runs all day. This suggests an error function of absolute deviation, but with saturation. Let's look at a fourth use case. Now, our temperature predictions are being used in television forecasts. Our viewers don't expect the predictions to be exact, so if they're off by a little bit, there's no penalty. This gives us a don't care region. There's no cost to being wrong by a small amount. However, if the temperatures are off by much more than that, the viewers become very upset, and they're likely to switch to another television station for their weather reports. A quadratic curve gives us the steeply increasing cost associated with this. Now, these are 4 fairly straightforward use cases, but we can handle even much more complex cases. Imagine that our top-notch business analytics team determines that our energy costs have a complicated relationship to prediction errors. Say something that looks like this. That's not a problem either. We can use that just as easily as any of the other candidates we've looked at. The only real constraint on our error function is that it doesn't decrease as it gets further away from zero. It can follow any pattern we want as long as it always increases or at least remains flat. The choice of error function makes a huge difference in which model will fit the best and what the parameter values for that model will be. Each one of these error functions would produce a different set of best fit parameters in our temperature model. The best fit curve will be different each time. Starting with the right error function can make a big difference in how useful our model is. The wrong error function can give us a model that's worse than useless. Keep your eyes open for squared deviation as an error function. It's a very common choice. So common, in fact, that inexperienced modelers might assume it's the only choice. It has some really nice properties for mathematical analysis, and for that reason, it's favored for theoretical and academic work. But other than that, there's nothing that makes it special. Chances are, it's not right for your application. Any time that you spend carefully choosing what your error function will be richly rewarded. Now that we have a solid foundation, in part 4, let's take a close look at splitting the data into training and testing data sets. It's harder than it looks. Most often, we are not handed separate training and testing data sets, but rather one big grab bag of data. When this is the case, we are responsible for splitting it ourselves. When we do this, we have to keep in mind that there are two different broad categories of generalization: interpolation and extrapolation. Depending on which we're interested in, we will divide the data differently. An example of interpolation is if we want to estimate the value of annual temperatures that we're missing from the middle of our data set. In this case, we know several values, both before and after. An example of extrapolation would be if we wanted to make estimates outside the range of our original data, either for dates that come before or dates that come after. Another type of extrapolation would be applying the pattern to a different town nearby. In both cases, we would try to infer something about the world that extended beyond the reach of what we had measured. If we wanted to divide our dataset to test for interpolation performance, it would be straightforward. We could randomly sort every year's data into one of two bins, testing or training. This is what we did in part 1. However, if we wanted to divide our data set to test for extrapolation, that would require a little more subtlety. If we were interested in making predictions about the future, for instance, we would have to make sure to test the model on data from the future that it had never seen and never been trained on. Otherwise, it would have an unfair advantage. Knowing what the temperature will be in 2 years helps to make a better prediction about what it will be next year. Knowing future years' temperatures would tip the model off to any upcoming trends or changes in temperature pattern. Most importantly, this is an advantage that the model will not have when we put it into practice making predictions. To honestly split the data into training and testing sets for extrapolation, we would have to divide it by date, training on all the data that came before and testing on all the data that came after that date. This would give us a more realistic assessment. More generally, when dividing data into training and testing sets, we want the data in the testing sets to be independent of all the data in the training set. Otherwise, it's not a true test of the model's ability to generalize. There are subtle ways that data can be dependent on each other, ways that knowing some bits can give you an unfair advantage when trying to predict other bits. Determining what constitutes independence often requires some domain knowledge. For example, if we wanted to test the generalizability of our model, we could test it on the temperature data from another town. But we would have to be careful. Our model's ability to predict the pattern in annual temperatures for a town that was only 1 kilometer away wouldn't be sufficient. That data would not be independent. 1 kilometer is so close that the two towns would share not only underlying weather patterns, but also the hyper-local weather quirks. Using measurement from one to predict the other would not test the model's generalizability. However, if we tested the model on temperatures from a town that was 100 kilometers away, that might be far enough away to be considered independent and would provide a better assessment of the model's generalizability. The ultimate measure of whether a train-test split is appropriate is how the model will be used in practice. Is the training-testing split representative of the conditions the model will experience when it's implemented? If so, you're good to go. If not, your testing error might be artificially low, giving you a false sense of security about how well your model is performing. In high-consequence applications, being blind to your model's weaknesses can lead to some very uncomfortable situations. Taking a close look at how you split your data into training and testing sets can save you this pain. So now that we've covered the preparatory steps, join me for part 5, where we talk about how to choose model candidates and how to handle hypothesis-driven and theory-driven modeling. Finally, we've reached the question that probably brought you here. What models should I try to fit my data with? In part 1, we stepped through the process of choosing a model. Train all the candidates on the training data, evaluate them on the testing data, and the one with the lowest testing error wins. The goal of this exploratory analysis is to find a concise representation of the patterns in the data, without regard to what form they take. This process helps us avoid overfitting. That is, finding a model that captures too much noise. However, it doesn't protect against underfitting. It doesn't guarantee that the model we found is the best one possible. There might be other models out there that would capture the signal even better and result in a lower testing error. We have no way to know unless we try them all. However, we have to balance this with the fact that there is literally an infinity of models to choose from. There's no way to try them all. It's not even practical to try the most common ones. Running them all in all their published manifestations is likely to take so long that we don't care about the answer anymore. And that's not even considering the time it would take to get them all running in the same code base. We're going to have to make some tough decisions. Despite these practical difficulties, the try-them-all approach is conceptually sound. The AutoML community is committed to making it feasible to try a lot of models at once. This is a great way to make sure that you're getting a broad selection of different model candidates. But it's important to keep in mind that for every model candidate included in an AutoML library, there are a million that aren't. With that one caveat, AutoML is a great way to balance time with the breadth of your candidate pool. One way to describe a model's complexity is to count the number of separate parameter values that get adjusted during model fitting. These are all quantities that need to be inferred from the data. It doesn't make sense to try to learn 50 parameters from 10 data points. For a well-behaved and responsibly fit model, it takes somewhere between 3 to 30 independent measurements per parameter. If we consider 10 to be a nice middle-of-the-road guideline, that means a model with 100 parameters would require at least 1,000 data points to fit well. This also assumes that the data points are scattered relatively evenly across the range that you're trying to model. If, as is more usually the case, there are dense clusters of data points and vast wildernesses around them containing almost no data, then the amount of data you may need might go up much further still. Using this guideline, a straight line, which has 2 parameters, would require 10 data points to fit confidently. That's 20 measurements in all, 10 of x and 10 of y. Multivariate linear regressions can have dozens of parameters. Random forests can have thousands. And deep neural networks can have millions. The number of data points you have can be a dominant limitation on the types of models available to you. If you only have 100 data points, it just won't be worth your time to try training a deep neural network. Sometimes we have a good reason to try only one type of model. One such case is when your research community has reached a consensus about which model is the most successful in a certain application. For example, in the problem of image classification, very particular architectures of convolutional neural networks have been shown to be quite successful. It's completely reasonable to repurpose one of these without doing a broad comparison across different models. The number of possible models in the universe is so large that it is vanishingly unlikely that a particular published convolutional neural network is the best solution to your problem. However, 1,000 diligent PhDs trying tens of thousands of variants have failed to come up with anything much better so far, so it's not a bad place to start. Sometimes it's safe to stick with a single model because we are highly confident that it reflects what's going on in the world. For instance, imagine that we're watching a baseball game and we'd like to predict where a pop fly is going to land. A naive approach would be to measure the position and velocity of the ball many times per second for every pop fly for many hundreds of games, and then fit all that to a model predicting the final location of the ball. A shortcut to this process is to rely on all of the people who have already made careful measurements and predictions about objects flying through the air and have found a beautifully concise model to describe them. In its simplest form, a ballistic trajectory model in 3 dimensions has only 6 parameters. A single observation of the ball gives us values of 6 different measurements: position and velocity in the x, y, and z directions. Depending on our measurement accuracy, 2 or 3 observations might be enough to accurately determine the final location of the ball. This is probably why veteran outfielders can catch a brief glimpse of the ball shooting into the air, then turn their back to it and sprint toward where they know it will land. Incorporating domain knowledge wherever we can is a great way to limit the set of models we have to consider. And often, it helps us make confident predictions with many fewer data points. Reason to try only one model: testing a hypothesis. If we're looking at our data in order to answer a specific question, as is the case when we're testing a scientific hypothesis, then the model only needs to be focused on teasing out that particular information. In this sense, a model's like a spotlight. Each model is capable of revealing different aspects of the data. By choosing a particular model, we're effectively asking a particular question or set of questions of the data. When we're testing a hypothesis, that question can be very pointed. For instance, the classic, "Are the means of these 2 samples significantly different?" question suggests a very specific model. Other more complex hypotheses might result in more complex models, but the connection between the form of the model and the hypothesis it is testing remains. Hypothesis-driven testing is well suited to clarifying the details of how our system works, or using data to help us make a decision. Hypothesis testing helps to shed light on a subtle point we've glossed over so far. One person's signal is another's noise. Consider our temperature data set from part 1. A climate change scientist may approach the data with one question: are the temperatures of the last 20 years significantly higher than the temperatures that came during the 100 years previous? In this case, a straightforward model that chops the temperature data into 2 samples and compares the means of both would be a reasonable approach. This is the signal they need to extract. All other deviation from this is noise to them. However, imagine another researcher studying the effects of solar radiation on climate. They would likely be more interested in identifying cyclical patterns in the temperature data. For them, any multi-decade trend would be noise. They would choose a model that isolates repeatable patterns on the 8 to 11-year scale. As we saw when we incorporated domain knowledge into our pop-fly model, making more assumptions allowed us to reach confident conclusions with a lot less data. This is part of a recurring theme in machine learning. Many decisions, of models, of methods, even of the questions we ask and the data we use, boil down to a trade-off between the number of assumptions we are willing to make and how quickly we want to arrive at a confident answer. The benefits of making additional assumptions are obvious. Reaching conclusions with just a few data points can save a great deal of effort and money. However, the downside is considerable. Each assumption is a potential point of failure. If that assumption happens to be wrong, then we could end up very confidently reaching a conclusion that's entirely false. This might be embarrassing in the case of an academic publication, or it could be catastrophic in the case of predicting severe weather events. More assumptions get us started fast, but they also put strong bounds on how far we can go and how much we can learn. When we make fewer assumptions, we give the data more latitude to tell us its own story and to reveal patterns that we hadn't anticipated and to answer questions that we hadn't thought to ask. Unfortunately, assumptions are a Faustian deal we can't escape. The essence of inference requires some basis for using the observations we've already made to set expectations about the ones to come. And every method for doing this comes with its own collection of assumptions. Some are explicit and some are quite subtle, but no method is entirely agnostic. And it gets worse. In practice, we're further constrained by how scarce our data is. We are often forced to rely on assumption-laden domain models simply because it's prohibitively expensive or entirely impossible to gather additional data. And so, we forge ahead with as much grace as we can muster, staying aware of the limitations we've knowingly self-imposed, and keeping in mind that our analysis is only as strong as our poorest assumption, staying vigilant for hints that any one of them is irredeemably wrong. On that note, let's look at some other assumptions that can prove useful. A lot of statistical models get their power from additionally assuming that the noise has some particular properties. For instance, that it's normally distributed, identical, and independent for every measurement. With these assumptions in place, statisticians have been able to derive powerful results. For several families of models, you don't need to have testing data at all. Student t-tests, ANOVA, and other statistical tools are a way to get around having to do separate training and testing. They make assumptions about the underlying model and noise distributions, and then use these to estimate how the model would perform on many hypothetical test datasets. They trade assumptions for inferential power. They are particularly helpful when you have few data points and can't afford to divide them into testing and training sets. Based on the training data and fitting errors alone, you can tell, to whatever level of confidence you want, what range the testing data will fall into. Even though this statistics-heavy approach looks very different on the surface, it's just another way to do what we've been doing all along, finding the model that best captures the signal and determining how well it generalizes. The difference here is that the generalization performance is estimated rather than measured directly. Step carefully. Many of the common statistical assumptions, independence, identical distribution, normal distribution, homoscedasticity, stationarity, they're routinely violated by the data that we work with. Some violations are consequential, and others aren't. But if you turn a blind eye to them all, you're likely to get poor results. So here's a tip. If you want to be a thoughtful colleague, you can help your fellows carefully think through the standard assumptions and figure out whether any of them need to be double-checked in their analysis. An anti-tip, if you want to be a statistics asshole, point out to everyone that their entire analysis is invalid because their assumptions are not all met. Sometimes when incorporating domain knowledge into our models, we can comfortably assume something about the parameter values themselves in addition to the model structure. For example, consider a model of regional differences in income, broken out by profession. There are already nationwide income surveys by profession, and it's reasonable to expect that regional differences in the wages of, say, a carpenter won't be radically different than the national average. Maybe higher or lower by 50%, but not by a factor of 10. This gives us a running start. With this bit of prior knowledge, we can craft a distribution showing our best guess for what these wages will be before we report a single measurement. Then, using Bayes' theorem, we can cleverly use each new data point to update this distribution. It's useful to think of this as a representation of our beliefs. We start with the vague belief that in any given region, a carpenter makes somewhere in the neighborhood of the national average. Then, as we collect data for each region, this belief gets updated and shifted and takes on the characteristics of the local data more completely. The magic of the Bayesian approach is that it reaches a confident estimate with fewer data points than it would have taken otherwise. Again, we have the option to trade some assumptions for increased confidence. Again, the pitfall is that if we start out with the wrong assumptions, we can actually make our life much harder and require many more data points to reach the same level of confidence. Those who favor the Bayesian modeling approach and those who don't trade usually good-natured criticisms and jokes. But it's important to remember they just represent different sets of assumptions. Each one's appropriate for different goals and different data sets. Another type of structure we could add to our models is causality. This is extraordinarily helpful for answering questions about why something happened and what would have happened if another decision had been made. Causal relationships are in a class of their own. Most statistical and machine learning models don't say anything about causality directly. They can at best hint at it through careful experiment design, but there's a small and growing body of work around models that explicitly represent causal relationships. They let you answer questions like, what if I had not made this decision? What if this event had not happened? These are called counterfactuals. And as you can imagine, this type of analysis lends itself very well to making decisions and evaluating them. If you want to go deeper into this topic, I recommend The Book of Why by Judea Pearl. He's a pioneer in the field and gives an excellent in-depth tour. Causal relationships are similar to the other assumptions that we've discussed. If you're justified in assuming them, they add a lot of power to your analysis and help you reach confident conclusions more quickly. However, if the assumption is unjustified, making it will hurt you more than it helps you, no matter how much you like the results. So, returning to the question at hand, which model candidates should you try? The answer, as always, is entirely dependent on what you're trying to do. But the one invariant, your single guiding principle in this process, is to be mindful of your assumptions. You can't get rid of them. If you ignore them, they'll bite you. But if you pay attention to them and thoughtfully prune them, they'll repay your attention many times over. Nice work. You made it all the way through. Now you're armed with the concepts you need to choose good models. May they serve you well in your next project.